Hello, welcome. Let me introduce Babak Hodjat. He is the CTO for ATI at Cognizant, where he leads a team of developers and researchers bringing advanced AI solutions to businesses. Babak is a former co-founder and CEO of Sentient, responsible for the core technology behind the world's largest distributed artificial intelligence system. He was also the founder of the world's first AI-driven hedge fund, Sentient Investment Management. He is an expert in numerous fields of AI, including natural language processing, machine learning, genetic algorithms, distributed AI, and has founded multiple companies in these areas and has 31 granted or pending patents to his name. Without further ado, let me introduce Babak.
Thank you very much, Kevin. I'm going to share my screen and jump right into it. Here we go. Okay, so we are going to be talking about explainable models, what they are, and some terminology and different types of explainable models, why they're important in the first place. And then I'm going to introduce a white box approach that is explainable, and we're going to walk through that as well. So white box, black box, what are we talking about? As many of you probably know, a lot of AI systems and data science models are black box, which means a query comes in, we don't quite know what happens, even the designer doesn't quite know what happens, and there's a response that comes out. How do we trust these models? Well, we actually verify that they work, they're accurate enough, they hold out data sets and so forth, and they do well. But there's some magic going on here, and we don't quite know what it is. This is an even bigger problem these days because the state of the art in building models in AI is now neural network based, and deep learning is inherently black box. Here's an architecture of a deep learning system that we evolved automatically. You can see that the architecture itself is quite complex. So the input coming in from the left-hand side goes through many, many permutations and iterations and so forth until it pops out on the right-hand side. And for example, in this case, some classification of chest X-rays is made. These are deep for a reason, and we don't quite understand what they do. But it's not restricted to deep learning based systems. Traditional models are often black box as well. And in many use cases, they're even preferred. For example, on the right-hand side, I have a random forest. It's a collection of trees, and it kind of, very roughly speaking, switches between these trees depending on what we're looking at. These are decision trees. Or boosting models like XGBoost, where you have some sort of clustering that's happening, and you're again classifying between the clustering methodologies. Very difficult to explain why a certain classification was made in these types of methods. But explainability is important. It's important for a variety of different reasons. Here are a few. For example, we want to protect against unforeseen behavior. If we had a way of knowing how our model is making a decision, then we might be able to protect against decisions that it might make out in the wild that we didn't expect or we weren't sort of comfortable with. That is the definition of a model, right? If all we expected from the model to do exactly what we expect in exactly the same situations, then that's not very interesting. We want it to be able to operate in situations and on data that are unexpected and we've never seen. But we don't want it to behave unexpectedly. Same thing goes for risk, or maybe that's a subset. What if scenarios where it's a rare set of data that's coming in, a rare context, a rare situation, and our model might, in those rare occasions, cost us a lot of money because it takes some sort of a risk that we weren't expecting. Can we kind of prevent that risk by having a perspective as to how it's making its decision. And of course, very importantly, undesirable bias. There are, desirable bias is fine, and it's actually how machine learning operates. But undesirable bias is when our machine learning system is actually making decisions based on data or relationships in the data that we don't want it to be using as a basis for its decision making. And hopefully I'll show a few examples of this as we go forward. So protection against certain behavior, that's one category. Enhancements. So if we had a sense of how our model is operating, we would get a path as to how to improve the model. For example, what are the features that are more significant? And maybe that gives us a clue as to collecting more data or expanding the feature set in that particular direction. So it makes it more useful and we get better results from our model. And so that also leads into augmentations and enhancements in future iterations. Also, for example, making sure that those features that our model is triggering off of are better collected, they have better quality, all those sorts of things. Those are all potential enhancements that we can make if we know that these are the features, in fact, that the model is using in various different situations. Explainability is also important because in many cases it's either regulated or it's required. We have instances in insurance, for example, underwriting, where this is absolutely regulated. In healthcare, for example, explainability is there. Europe has a whole explainability set of regulations that's come out. By some accounts, there are other industries too that are either very enthusiastic and interested in explainability or are on the verge of having regulations around them, manufacturing being one of them. If we could explain why a part is defective or is breaking, then we can have a better means to go fix it or prevent it in the future. For self-driving cars, for example, if we know why the car is behaving in a certain way, we can enhance it in that manner. So very, very important there as well. Whether or not, for example, even our system is abstracting or overfitting in certain instances can be something that we can derive if we had an explainable model. Okay, there are approaches to help with explainability. Most of them are somewhat unsatisfying. Here are a few. For example, the easiest thing we can do is measure correlations and variable importance. So we have a number of features that are coming into our model. Let's, figure out which ones are more correlated to the output of our model. If the model is a black box, then this will help us get a sense of which variables are more important. However, it's very gross level. It's telling us something about the model. It's not necessarily telling us something about point predictions that our model makes. And it's sort of a summarized view. One version of this is this SHAP value, which is based on Shapley values. Essentially what it says is, if I have a number of features, if I remove one of the features, how much does it impact the accuracy of my system? Now, we're getting a little more accurate now because we could at least look at certain different instances and see where for each instance the variables fall as far as their impact. In this case, for example, this is to look at whether or not a cyst is malignant. And the three variables that seem to have the biggest impact are perimeter, compactness, and area. And you can generally get a sense of where and when those three, maybe symmetry to a lesser extent, are impacting us. But it's open to interpretation. Where are these variables used? In what combination do they become significant? After all, if it was as simple as just correlating variables to outputs, we wouldn't have to go through this whole process of building these complex models. So, something gets lost in this sort of explainability for these models. For more sophisticated problems and models, such as deep learning, a class of explainability which is more or less deep learning specific, are a class where we interrogate after the fact the deep learner. So we have a fully trained deep learner, and so we show it an image, for example, in this case, a chicken, and then we look at intermediate layers and how the neurons are firing, and get a sense of which parts of the actual image is the deep learner actually triggering off of, more so than others. And you can see there's a sort of a silhouette of a chicken, and there's certain characteristics of the chicken that are highlighted, which makes this a chicken as opposed to, let's say, I don't know, a crow. So yes, very interesting, not comprehensive, and still we might miss out because this is translating it into something visual. We might miss out on certain characteristics of, in this case, images that are significant, that are not highlighted, or we visually don't quite get. Finally, there is a class of methods that I've seen actually used, for example, in insurance, where we actually train a deep learning network, for example, on our data set. And then once we have that deep learning model, we then train a simple explainable model against a deep learner. And this training, for example, could be a single layer perceptron, which is considered to be explainable. And the behavior then roughly mimics the behavior of that teacher model, but now you have an explainable model to substitute, and you can make use of that. Again, it begs the question, how much can we trust this second model? Especially if that second model is linear, but there are, for example, non-linearities that the teacher model is exploiting and get lost in this whole translation. Then it also begs the question as to which one of these two models are we going to actually take out in the wild and actually deploy. This is interesting because you could think of various creative ways of deployment. For example, you can deploy both, and in cases where they disagree, revert to one versus another. So it does give you some interesting avenues and ways to make use of this explainable substitute. At least in some cases, you will be able to explain what's happening. Okay, there's another class of methods that are inherently white box. So once we actually train, and we just alluded to one, which is a single layer neural network perceptron, when we train these models, the model itself is explainable during training and at the end of training. Some good examples is, for example, learning decision trees. This is somewhat explainable. We can just look at this tree, and it tells us, for example, that if the bare nuclei is less than -0.28, then check the uniformity of the cell size, and depending on which side of 0.42 it falls, then it's either benign or malignant. So we kind of get a sense of how it is viewing the world. It's linear, not very powerful, not very expressive, nor accurate. But I can tell you right now that in many cases, while there are better methods and more sophisticated methods for solving problems, people have to revert and fall back to, for example, decision trees, simply to checkbox the explainability checkbox. So it's very important to note that these models are in use, and they get chosen simply because they are explainable. I've listed a number of other methods that could be thought of as explainable inherently. But today I want to focus more on an area where I've worked on a lot, which is using evolutionary computation. Evolutionary computation is very interesting. It could create you explainable models. It could create you black box models. The reason for that is because it's a meta-learning algorithm which is agnostic to the representation. So depending on what kind of representation you use, you can create explainable or non-explainable. Let's just venture into briefly talking about evolutionary computation. Many of you are familiar with evolutionary computation simply from genetic algorithms, for example, which, by the way, are inherently not explainable. What is a evolutionary computation system do? Well, we have a representation. In this case, I took a website. This is a web page, and I'm just using that as a representation for an individual. I want to change the design of this web page. So what we do is we create a population of alternatives, various different permutations of what a web page might look like. The environment is presumably, showing it to users, having it deployed. And then, we kind of observe how well it does, and then we make some changes to it. Next, we create a next generation of the population. Again, observe how it does, rank order, create a next generation, we go forward. As I said, that representation could be a neural network, and a neural network is inherently not explainable. But we could use that, and then in actually generating the next generation of the population, we can take, for example, the list of weights in the neural network and take them, the two parents that are doing better in the last generation, and cross them over. So take some of the weights from one, some from the other, and create two offsprings by mixing and matching. And now I have a new offspring in here. And through that multiple generations, this population starts usually converging towards better results. I mentioned genetic algorithms. The representation there is a bit string. And, we have this concept of a gene, a chromosome, a population. Again, you pick a point and you swap part of this bit set with another, and, create offsprings and put them back into the population for evaluation. We talked about the website. Let's say we have a web page and it has a number of different places where we can afford to make some changes, such as, where is the header text alignment? What is the button stroke? What is the button alignment? All that kind of good stuff. Even with this many permutations, you actually have more than 10,000 combinations. You can't simply A/B test your way out of designing a better page here, better in this case defined by a conversion rate, for example, for the page. How does the system work? Let's say we initially just generate a whole bunch of different pages randomly to get maximal coverage over the search space. And then we let all of these pages sort of get some traffic and measure the conversion over some amount of time, statistically significant enough for us to be able to rank order and relatively rank order them. And then we pick two parents that are doing relatively better, and we take bits and pieces of the two parents and mix them into child AB and child BA. The reason why I wanted to show this is for you to get a sense of how evolutionary computation works. In this case, it's very visual. I'm actually using parts of the design for parent A and the remainder from the design of parent B and putting them into a web page. So it's very clear what that web page starts looking like. And that's the representation. The representation is literally what is presented to the users. Well, okay, now we take these children, place them back into the real world for traffic to hit them, and we get another sense of how they do. And through multiple generations, we see the pages that look like are doing better coalesce around these sort of clusters of design. And this tells us something about which design elements seem to be doing better for us. And you can think of this as sort of an inverse binary search. We kind of know that there was something in parent A or something in parent B that set it apart from the other guys here. So in order to find out exactly what combinations of changes set them apart, we kind of put them back together or mix them into child A, B, and BA, with the hope that we actually were lucky with one of these children and we actually captured the best of parent A and parent B. And through generations, we do better. Okay, let's very quickly look at what this looks like. Here's a web page, for example, an actual web page for which we did this. It's an education program. We want to sign people up through this little widget. We want to get the best possible conversion rate. There is some sort of, control conversion rate through time. Let's see as we make changes and like evolve the web page, whether we can get better performance. I'm showing you the best design so far, and you can see as we go through these, a couple of things happen. One is the best design so far keeps getting better, but also this blue line, as opposed to the control line, is better by about 12%. So as we're actually searching, the entirety of the pages that are shown are doing better than the incumbent design. Okay, so evolutionary computation in this case worked. And if we put it side by side, this is the winning design, this is the incumbent design. It's made a bunch of different changes. Obviously used really eye-catching color for the widget, but also changed some of the text, over the fold, below the fold kind of changes and so forth. And the entire thing actually resulted in 45% more conversions. It only took us 8 weeks to find this. And the possible designs were 380,000. Obviously, we didn't test 380,000 designs. We went in through a very small subset of that, and we still got better improvement. Okay, so that's another view on how evolutionary computation works. But what does all this have to do with explainability? We can take explainable representations and evolve them. In fact, John Koza was a pioneer in this in the 90s. And one of the approaches that he took was he said, okay, let's say I have some data and I want to do nonlinear regression on this data. In other words, I want to come up with sort of a equation that explains the data. I can represent the equation in a tree, and then I can do all sorts of reproduction functions on it. For example, I can do a crossover between two trees that seem to explain the data better, and I get two other trees. So actually, while I'm evolving this system, I am getting explainable results. It's an equation. I can look at this equation. I can look at what kind of variables it's using, what kind of function it uses on these variables, and what are the relationships. Now that's an equation. We could use another variety of this genetic programming methodology, which is rule-based approach. In this case, we used a rule-based, we evolved a set of rules, basically. So this rule set was automatically authored by this evolutionary computation system in order to help us predict and prevent severe drops in blood pressure, arterial blood pressure, for patients in the ICU. The approach was interesting because the practitioners needed about 30 minutes of a head start. So there was a 30-minute blackout window, and the rule set had to actually predict whether or not the arterial blood pressure goes above or below the normal level after 30 minutes. You can see the rule that it had, the rules here are explainable, and we can actually look at some constituents of this rule set that get evolved. So we have some conditions. These conditions result in actions. In this case, the actions are sort of a prediction of what's going to happen. There are strings of conditions that are stringed together. Then each one of these, which is a set of conditions plus a corresponding action, is called the rule. We have a set of rules. Sometimes we have default actions as well. So if we go through all the rules, none of them fire, there's a default action. What do we do about features in this case? So how do we decide what features to use? The good news is there are approaches that allow us to automatically discover these features as well. For example, the arterial blood pressure readouts are point readouts that come in and if we define a window, I think we took a window of 30 blips of the readout, and then we define various different statistical functions on these windows: kurtosis, mean, max, min, and so forth. So now we automatically actually have a set of features to work with. And what's nice about evolutionary computation is if that feature gets picked up, then it's probably significant. If it doesn't, then you kind of know that that feature is probably not very useful. Just to get a BNF form for the rules, here's another way of looking at the grammar for the rule sets. And basically what we do is we evolve this rule set. We take rules from one parent, a few from one parent, a few from the other. That's kind of could be one way of crossing over. Another way of crossing over could be taking one rule and sort of multiplying it logically into all the other rules. You could remove rules, you could add rules, tweak rules. That would be a mutation. You could take a rule and swap the action in. So there are many different reproduction functions you can actually apply on two parents in order to derive a new rule that you think might be more effective. You can make them more general, you can make them more specific, and by virtue of doing that, hone in on what is the rule set that works best. Okay, so let's look at a few examples of this. And through these examples, hopefully see some of the interesting attributes of an explainable system. Here's a very simple example. It's a cartpole. So we want a set of rules that literally move this cart so that the pole is balanced, so the pole doesn't really fall over. And the starting point is random. And what's interesting here is we've actually evolved this rule set. This rule set is straight out of the evolutionary system, and it's found a cube relationship between two of the sensors. So that's saying something to us about the physical world, at least the physical world of this cartpole. And it's useful. It's an abstraction that as humans we can understand. Now, this is a very, very simple problem. Here's another game. Some of you guys have played Flappy Bird. We want to either flap or no flap, like hit the space button or not, for moving through these pipes. If we hit a pipe, we die. And you can see here that, again, the system has come up with a set of rules that have found relationships between various different sensors. We can even know what these sensors are: next pipe distance to player compared to next pipe bottom. That's some relationship and more. And then that tells us the bird whether to flap or not to flap. And there is a default action of not flapping, and it solves the problem. There are other more probably useful use cases. In this case, diabetes. So we want to not only diagnose, but also prescribe medication for diabetes. And we want to do so with multiple objectives. We want people to be discharged from the hospital, but not any kind of discharge. We want to make sure that they are discharged alive, not dead. And we don't want them to be readmitted. So that while they might be discharged, we want the sort of cure to be kind of more permanent, so they're not readmitted back in. So there are multiple objectives we have here. And let me just jump to a set of rules here. This is a set of rules, again, that we've evolved that gives us a means to do this diagnostics. So we need to be careful, because this set of rules, as a layman, I look at this and I don't quite know what it's doing. But we took this set of rules, which is actually quite accurate with the data set that we ran. And we showed it to a practitioner, a physician, and they told us this is what's happening. Immediately after we saw this set of rules, we were alarmed. Why is it looking at, for example, whether this individual is Asian, or whether the age is between 60 and 70. We're uncomfortable. If our rule set is doing something like this, is this unwanted bias? It turns out that this is fine. It turns out that for diabetes, it's okay, because different medication works with different races, different age groups, whatever, and it's okay and it's acceptable. But of course, this highlights the fact that explainability might be able to flag these sorts of things, which we should absolutely have front and center in developing our models. But this gets me to an interesting sort of side note here. Is explainability enough? In the cases that we saw so far, it felt enough and it was actually adding value. But here's a case that we did a few years ago, which was to actually train these rule sets to trade in the stock market, thinking that explainability is important for us to prevent risk, unwanted bias, give us a direction as to new features that we want to add into the system, all those sorts of things. And here's an instance. This is a robotic trader, and it's actually bought at the exact right time and sold at the exact right time, and we've made money. Great. If you guys want, I can show you the rule set that did this. This is the rule set. Okay, so what use is this? And I'm just showing a fraction. It's a very, very complex rule set. Maybe it's explainable, it's not quite understandable. So we do have this issue. Now, in this particular case, it's still useful because on a point-by-point basis, we can still get a sense of which rule it was that fired. And that particular rule that fired, at the exclusion of other rules that didn't fire, remember that these work hand in hand, give us a sense. For example, in this case, the robo trader was losing money to a certain extent, and volume changed in a certain way, blah, 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 and it decided to use a limit order at a certain delta of the last market price and then buy, for example, and then did something similar in selling. Okay, that might give us some comfort, but as a whole, I'm not sure if I quite understand the behavior of this robo trader just simply by looking at the rules. So I'm uncomfortable. But the system does work. It's making me money. It's doing well. So what is the root of what I'm looking for in an explainable system? Is it about blaming someone? For example, in self-driving cars, we know many of these algorithms do very, very well, and the incidence of accidents is much lower than humans. But we're still not comfortable with them. Why? Because when a human's making a mistake, we can always blame them after the fact for the mistake, whereas it's difficult to find the culprit when it's automated. Is that really the core of this? It is about trust, though. This is ultimately about trust. And I want to make a case here that explainability is only part of trust. A more direct method to tackle the issue of trust is to actually measure it. So if we have a second model that can sit side by side with the first model and tell us on a case-by-case basis how much we should trust the system, aren't we directly tackling the trust question without necessarily needing an explainable model? This is done, for example, by creating Gaussian programs based on residuals on the input and the output of an pre-existing model, trained model. And based on those residuals, we kind of get a sense of, for a certain set of inputs, how different is that set of inputs from what our model is used to seeing? And then on the output, how different is the output of our model to what we're used to seeing in the past from this model? And if we combine those into this Gaussian program that we train on the model, then we can actually get a certainty distribution on the model, so that point for every input into the model and the output from the model, it can tell us how much we can trust it. So that's one approach. In fact, the approach is so interesting and accurate that if you actually move, once you create this certainty model, if you move the output of your original model to the mean of the distribution that the certainty model is giving you, you can actually improve the behavior of your original model. And we did that. So we took the state of the art a few years ago of a celebrity age estimation, and we didn't change it. We just took that model, a black box model, dense net, very, very difficult to explain. And we used a certainty model side by side with it, and then we moved the output of that model to its mean. And we actually improved the state of the art by 6.35 on the mean absolute error. Significant improvement simply by adding trust to the original model. Okay, there is an approach. The next speaker, my colleague Risto, is going to talk about this, that brings together a number of elements of trust into decision making, which is ultimately where we need all of this. So what do we mean by decision making? We're in a context. In other words, there's some input that describe where we are, who we are, what are we doing right now. And then we want to take an action out of a universe of possible actions in various different contexts. So we want to pick what permutation of actions to use in a certain context. Could be a classification, could be other more sophisticated actions. And we're optimizing for outcomes. Could be revenue versus margin, could be accuracy versus cost. So we have some outcomes. So what if what we do is we create a predictor model that, given any action context combination, so a decision, will tell us what the outcomes are going to be. So that's a predictor model. Then pair it up with a prescriptor. Actually, even train the prescriptor against the predictor model as a surrogate. And the prescriptor then tells us what actions to use for any given context in order to achieve an outcome. So now we have a system that tells us what to do in every situation in order to achieve an outcome. Already there we have one level better sort of trust, because we're not just taking the actions of our prescriptor on face value. We're saying, what would happen if I do what you tell me to do? And the system says, well, here's the outcomes that you can expect. Okay, let's put this together into an entire system. We collect this data from the past decisions. We create this predictor that takes context in action, any context in action, and can tell us what the outcome is. We use it as a surrogate. We create a prescriptor. We can use evolutionary computation to do this because it's efficient in very large search spaces. And we create this prescriptor. We also create a certainty model. So now we have many of these elements of trust in a decision system, where the system tells us what to do, tells us what's going to happen if we do it, and tells us how certain we can be in it. And then we can apply that in the real world. And as new data comes in, we can retrain predictor, prescriptor, and certainty model. And of course, our decision maker, if it's a human here, can always interrogate the system. They can always take the set of actions and say, what if I do something else? Well, if you do something else, the predictor can tell you what's going to happen. And our certainty model can tell you how certain you can be in that new outcome prediction. So there is a form of interaction there that can give us a little bit more trust too, where possible. And not all decision systems have a decision cadence that can have a human in the loop, but where possible, this can add trust. Let's look at one last demo, or at least screenshots of a demo that brings all these elements of trustworthy decisioning together. This demo is interesting because the decision has to do with actually assigning humans to a certain task. So we have a few inspectors or investigators, and the most important decision for us is which one of these investigators to assign to a certain investigation. In this case, it's an accident, and we, as the insurance company, we need to assign an investigator for subrogation, so that they can investigate whose fault it was, and then that helps us with the negotiation with the other party's insurance company. And so the one element of trust is overall show your users what is your overall performance. How well have you done so far? How successful? What percentage have you improved successful reassignments, for example? So have a dashboard that tells your user how well you've done so far. That increases trust. Then, of course, are the other elements, which is, for example, the system is telling us to assign this particular investigator. And it's saying that if you do so, then the probable recovery dollars is 60 to 80% of total. And you will recover, the time to recovery is 0 to 5 months. Great. And it's giving us a confidence value. So we have that point certainty. In this particular outcome prediction, we know we're about 89% confident. Okay, and then there's the interaction. What if instead of this investigator, I were to choose this investigator? Okay, we'll run this through the predictor and tell you that the recovery dollars now is going to be less than 60%. And you're looking at a longer time to recovery. But our confidence in this outcome is lower. So if you want to go with this one, you're taking a risk, but you could be mindful that this is kind of out of scope for what our model knows. Finally, we've talked about multiple outcomes. In this case, we want to maximize the dollars that we recover while minimizing the recovery time. Maybe if we gave the investigator more time, we would be able to recover more, but that's more cost to us. So we can actually give the decision maker here, or the boss of all the decision makers here, a say as to what balance of maximizing dollars and minimizing recovery time they would like. So if they move this button to the left, they're going to recover more dollars, and maybe right now in this economic climate, this is more important to you. So do that. Once you do that, every single decision recommendation that the system is giving to the decision makers is going to aggregate into this balance of maximizing dollars and minimizing recovery time. It's multi-objective, and evolutionary computation is very good at exploiting multi-objective search spaces. Finally, counterfactuals. Tell your user how well you did in the past, as opposed to the decision that was actually made. Now, the system that I showed you does not have that functionality. This system, which is a demo that my colleague Risto is going to give and talk about in the next talk, does. It's called counterfactuals. In the next talk, we will talk about how a decision system like this can be built around recommending best intervention policies for COVID-19 for different regions in order to reduce the number of cases while also kind of reducing the economic impact. So let's say I am a decision authority in a certain region, and I've made some decisions in the past. What if I want to go back to a certain date, let's say January of this year, and check to see, with the knowledge that I had and the decision I made back then versus the decision that the system would have made back then, how well would I do? In some ways, you can think of that as regret. What is my regret? Or did I do better? So you want to give a facility to your decision makers to be able to check these counterfactuals. Obviously, you want the counterfactuals as part of your whole process to validate the approach as well. I'm going to end on a slide that I don't think Risto is going to show about this particular application and kind of bring it back full circle to explainability. That same system that allows us to know what to do, what actions to take, such as school closure, workplace closure, contact tracing, facial covering policies, and so forth. What should we do for a certain, in this case, Florida region, in order to reduce the number of cases while reducing the number of policies in place, which is a place sitting in place of economic impact. And I can actually evolve a set of rules that can show you this. The demo that Risto is going to show is not rule-based. It's actually using a deep network for that. But here we've actually evolved a rule set. And so it's explainable. The accuracy is comparable to the deep network-based system. And we can actually derive various different things. If we look at this at various different context elements and why and what it's actually giving us as far as the action recommendation, it gives us a sense of how the system's working, especially in cases where there is some of these rules fire for a certain case, and we can look at what those are. So to summarize, in considering the AI's recommendation, we want to know what the overall performance of our system is. We want to be able to predict the consequences of the decision. We want to get a sense of point certainty. Don't rely on the softmax of your neural network output. That's notoriously bad. Use another sort of specialized model for that. We want to be able to interact and throw what-if scenarios against our model. And that gives us some sense of comfort as to how well it's doing and whether or not what it's suggesting to us is indeed the best that we could take. We want the system to be able to select from a balance of multiple objectives. We talked about some of those examples, such as, recovery time versus the amount of dollars. We want to have counterfactuals so we can actually try out past history and kind of check on regret. Explainability is important because it gives us a sense of how our model is operating. And here, again, I would highly recommend looking at white box explainability systems. And finally, ethical considerations. I'm not going to talk a lot about that, but it is at the heart of a lot of what we worry about these days with AI systems. The only thing I'm going to say here is let's make sure that ethical considerations don't translate into, oh, let's find a scapegoat. Let's find a human to blame, because that really doesn't solve the problem. It just gives us the satisfaction of revenge in some ways. Let's make sure that we have a measure for the unwanted bias that we want to reduce. And in the case where we have the luxury of being able to find a balance of outcomes, let's set that as an objective. So that's one way. I'm not saying that's the be all end all, but that's one way of being able to incorporate some ethical considerations into our system. With that, I'm going to take any questions that you guys might have.
Actually, I do have a question for you if it's coming through. Let's just say you're creating a model that determines whether or not you want to hire somebody, and the firm's counsel comes to you and goes, can you explain in court whether or not we're using any protected information on this hiring decision in your model? How would you handle that? And one method I've heard of is, well, so you starve the model of that type of data. Is that a good method, or would that cause other problems?
Indeed, the first reaction that we have to these sorts of problems is, let's not have the data in there in the first place. It works. It works, but you never know, right? It might be that the bias is not easily attributable to a certain feature. So you might actually remove the feature that is shouting, oh, my race. Okay, yeah, that's bad. I'm going to remove that. But it might be that sort of decision making is sort of in some combination of existing features that belies race. We have this, not going into politics, but we do have this debate right now here in the US as well, where we're thinking, well, okay, we're not like blatantly using this kind of information to make some decision, but it's kind of like inherent in the manner by which the decision is being made. So I would always say, use that as a last resort, and don't think that, okay, I'm done because I've removed those. I would actually suggest, again, to be very clear about what it is exactly that you want to remove. That is going to help you either way. Whether or not you move to an AI system, it doesn't really matter. Because if there's bias in your hiring in your organization manually, you want to measure it anyway. It's not sufficient to just after the fact say, hey, this dude was a bad actor, and so I removed him and everything's fine. No. If you don't measure it, you're not going to be able to preempt it. Once you do measure it, I think an AI system can be set up to reduce that bias for sure.
Great. Thank you, Babak. That's all the questions we have for you.
All right, awesome. Thank you.